Oh, so you like, oh, yeah. Yes. Okay.
Hello, everyone. My name is Ilya Titarak. I'm the president of the Tallahassee Scientific Society, and I would like to welcome you here. Couple words about the TSS. Our mission is to advance the appreciation science. We leave the science itself to FSU and College of Engineering, but we're working on appreciation. And to that end, we have this great lecture series, Horizons, this last one this season. We have a monthly science salon lectures, third Thursday of every month, in a cozy atmosphere of Blue Tavern. That's a lecture. And then we put a lot of effort into K through 12, especially with focus on Title 1. So if you are into some volunteering or helping out, then, well, one, you can join TSS. Two, you can volunteer at any of our events with STEM outreach with kids. And then if you are at FSU and you need broader impact for your grant application, then we have all kinds of options for you, including Horizon lectures, science salon lectures, and volunteering. All domains. So enough about the TSS. Now let's introduce our speaker who gracefully agreed to talk today. Massimo Marengo got his undergraduate degree, which was master's right away, right? So
yeah, Italy is a little longer there.
Okay, yes. From University of Turin in Italy, and then got his PhD in astrophysics at CISA in Trieste, also in Italy, and then joined the Harvard Smithsonian Center for Astrophysics as a, guess what, astrophysicist, working on a team which launched and operated a Spitzer telescope. So half of you probably watched Irrelevant Astronomy Show. That's where it originates from. So, but then Massimo dropped his affiliation with IR2 and went on the bright side and joined Iowa State University as faculty and rose through the ranks of assistant, associate, and professor there. And then in 2022, we got very lucky that he joined FSU. And so now he's here, and then all the other details of his career, well, you will find out in a minute. Thank you, and join me welcoming us.
Thank you. Can you hear me well? Yes, the microphone. Okay. So today I want to try something slightly different because we're in a planetarium. So I thought maybe we should use the planetarium. So the first part of my talk, actually, I want to have all of you come with me for a stroll, and I want to go with you in some of the most interesting places that we can find in our galaxy. And there is a reason for that. We will see nebulae, we will see big star. There's also the big star exploding, but all those different places are connected into something that we call a galactic ecosystem. This ecosystem is the way that the universe uses to actually evolve, to go from the primordial stuff that you can find at the very beginning of the universe to what we find today, the elements that form Earth, the elements that form us. So those ecosystems are the way for the universe to go from the Big Bang to us. So let's see if it is working. The first time I try to practice. We start from right here, from Tallahassee. So we turn off the light. You should be able to see the night sky. More or less how we see it from here. You see? Yeah, it is. There was the sun. I said we have to take out the sun because we want to see the stars. So this is more or less what you would see in Tallahassee. Well, if you go into one of the more darker area in the city, and you see the main stars. But if you go in some place which is darker than the center of Tallahassee, then maybe you will be able to see better this, which is the Milky Way. Now, the Milky Way, is our galaxy. Is a collection of 100 billion stars that rotate around the center on the disk. The sun is one of those stars. But it's not just the stars. Even if you just look at the Milky Way, there are brighter area, there are darker area, there are nebulae, bright nebulae, dark nebulae. All those are part of the location that I want to show you today. And these are integrated in the system, which is the Milky Way. So the first one, the first place where I want to go is somewhere that you probably know because it's in one of the most visible constellation, even from Tallahassee in winter, which is Orion, the Hunter. And you see where there is this red cross. This red cross is the location of the Orion Nebula. It's a bright nebula. We can zoom a little on it. And the zoom will show us an image which was taken with the Hubble telescope. And this is quite impressive, but I wanted to show you more details because with this big telescope, we can actually see in very, very detailed all the typical components of those nebulae, star, the gas, and the dust. I will tell you in a moment what I mean with dust. And we have also computers that are able to extract information which gives the 3D spatial distribution of all those components. And this is how NASA made this video, which is a flyover inside the nebula. See, we are approaching the nebula, and you start to see that it's a 3D object. The stars that are projected on the nebula, in fact, are above it. This is the one that you see on the side. And the reason why I'm showing you this is because this is a stellar nursery. This is one of the places in the Milky Way where new stars are born. And the stars are born from the stuff that you see glowing there. What is the stuff? Well, there's a lot of gas, like hydrogen, helium, or complex molecules. And there is dust. Where dust is not the same as the dust that you find in the corner of your house. It's more like a little grain of sand. That's one kind of dust we have. Or something which is more similar to smoke, like little particles of carbons that are mixed together with the other kind of dust. From this material, the gas and the dust, stars are formed. And as we are flying over the galaxy, you see that we can start to see some of the stars which are very young and still in the act of formation, like this one. So this is what we call a protostar. The protostar is formed by the collapse of some of the gas and dust in nebula like this. They become very dense, so dense that in the end reach the condition for nuclear fusion. And when that happens, then the star is born. This is one of the components of the galactic ecosystem, places where stars are born. So I want to show you the next step, which is what happened after the stars are formed. What you get is a cluster of young stars. And without going very far from Orion, we can find a cluster of young stars, which I'm sure you know, which is Pleiades. Yeah, these are very easy to see in the sky. You just need to go in a place which is slightly dark. This is a cluster of young stars. I want to zoom a little so that you can see how they appear. Now, the stars that are in a cluster like the Pleiades are stars which are relatively similar to the Sun. They are low mass stars, meaning their mass is similar to the mass of the Sun. Maybe the masses are a few times the mass of the Sun. So we say that this is a young cluster, which is the result of a low mass platonic region. And you see that these are young stars. They're still embedded in the residual of this dust and gas that contributed to their formation, which is what formed this nebula that you see around the stars. Now, there are, of course, in the galaxy stars which have a much higher mass. They form in different kinds of star-forming regions, which is what we call the high mass star-forming region. And there are many. I mean, they're more rare than the places where, than the stellar nursery where stars of low mass are formed, but there are some of them. The one that is very pretty I want to show you is actually in the southern hemisphere, so we have to travel a little more. And so we go along the Milky Way, more. And then there is the constellation of Carina. And there is a dark spot there because those massive stars form really embedded in the denser, darker region of the Milky Way. And if we zoom on it, and it's best if we do that with the infrared, because the infrared telescope like Webb managed to see through the dust, so we can see what is embedded in it. But this is what we see. Now, this is small from here because it's far away, but with our telescope we can actually zoom quite a lot. So this is how it looks if you were able to almost step into it. You see the square here. That square is where those massive stars that just formed up. So this is a young massive stellar clusters. These are very bright star, very hot star. They emit a lot of radiation, even emit a lot of stellar wind, like the sun, but much stronger. And the result of that activity is that they kind of create a cavity inside the nebula where they are formed. And you can actually see those filaments here. Those have been formed by the pressure of the light and the wind coming from these massive stars. They compress the nebula around to the point that sometimes they manage to put this nebula over the edge, and parts of this nebula then collapse and form a new star. So what happened here is that you can have a sequential star formation. You start to form these massive stars, and the activity of these massive stars causes new generation of stars forming within the nebula. Now, those massive stars, they don't live very long. In general, the more massive a star is, quicker they burn to their nuclear fuel. They have more fuel, but they're so bright that they consume it very quickly. So when that happens, when they run out of fuel, they cannot support themselves anymore, and gravity takes over and they collapse. And I want to show you an example of that in Cassiopeia. Cassiopeia is also a constellation which is easy to see because it looks like a W in the sky, and this mark in the Milky Way. And you see that little dot there? Well, that is Cassiopeia A, which is what we call the supernova remnant. So these massive stars, when they run out of fuel and collapse, they do two things. One is, well, they explode, and the result of the explosion is the nebula that we see around, which you'll be able to see. Yes, this one. Another image from with the Webb telescope. So all this material that you see is the material that has been violently ejected by the star as it exploded. And then there is something else which you won't be able to see because typically you can see better in X-rays because it's very hot, but difficult to see with the visible light. There is the remnant of the star, which is a neutron star. Now, those two components are very important, and will come up later when we talk about how all this fits together. The ejecta of that constitutes the supernova remnant. This is what is a way for the star to return to the galaxy the material that has been processed by the nuclear processes, the nuclear fusion, the white one when the star was still burning, and then the violet one when the star explodes. It's a way of returning this enriched material to the galaxy. And this is another component of the cycle. Not all the material is returned, though. Some of it is kept in the neutron star, which is a very dense, very compact object. You can have the mass of the sun, of the sun or more, be 2 times the mass of the sun in the radius of a city block. These are very, very dense. Those also will have a very important role in the ecosystem of the galaxy. Now, stars like the sun, they don't explode like this. They just simply fade away, and I want to show you an example of that. So let's close this, and then go into the constellation of Leo, which is farther away. And there is a star that I want to show you, which is a very it's a star that you don't see with the naked eye. It's very faint. But it's a star which is a bit like the sun, but similar to what the sun will be when it's at the end of its life. It's called CW Leoni, so let's zoom into it. And now we're going to see the star through the lenses of an infrared telescope, so you can actually see it. And you see that it's fuzzy, but it's fuzzy because the star itself is completely surrounded by these rings, and these rings are the result of a slow ejection of material from the surface of the star in the circumstellar space. So these stars, they don't explode like massive stars. They don't do supernova. They just fade away, slowly shedding the external layers until what is left is just the core of the star, which is very hot, which is what we call the white dwarf. So even in this case, even for the low mass stars, still the stars at the end of their life have a way of returning to the galaxy the kind of element that they have produced thanks to their chemical nuclear reaction. What is left in the white dwarf is locked in, but not necessary. We'll see also that in the case for white dwarf, there are ways in which sometimes even the white dwarf manages to return some other elements produced with a completely different kind of nuclear reaction to the galaxy. And we will see in a moment how all these components are totally necessary if you want to understand how all the elements that we see in the periodic table actually came to be. Now, there is a final surprise, because stars like that one, and maybe like the sun, in fact, they have a final present that they give to the galaxy before finally dying. And to show you an example of that, I want to pan another constellation, which is to see the Lyra, which is the constellation of Vega, one of the brightest stars in the sky. So that's Lyra. And you see the cross, well, the cross is pointing in something that you already see. You can actually see pretty well with just a binocular. It's called the Ring Nebula. And if you look at the binocular, it looks like this, like a little circle on the sky. The visible, it looks kind of greenish. But if you use black, that's how it looks like. So this is a very brief instant in the life of the star. So after the star is almost about to dissipate completely, when the white dwarf is exposed, white dwarfs are very hot, maybe 10, 20, 30,000 Kelvin, which is like, say, Celsius, which is a lot of Fahrenheit, okay? So that radiation is so hot that actually ionizes this gas, this nebula that you have seen before has been shed by the star. And what you get is a planetary nebula. They were called planetary nebula because with the early telescope, they were looking like circle, like little planets. Nothing to do with planets. these are like the emission, the fluorescent emission of the gas that has been emitted by from the stars, and it is illuminated by the white dwarf, which is the object we see on the side. So these are the main elements that I wanted to show you. And now what I want to do is to try to put everything together so that I can tell you how those different components are part of a more general ecosystem and the way they manage to go from what the universe was at the very beginning to the universe that we see today. And for that, I need to switch on my presentation. And can I share the screen?
Yes.
Okay. Okay, so can you still hear me this thing? Sometimes I'm not sure you were hearing very well. Can you hear me well?
Yes.
Okay. So what I want to show now is how all those elements fit together in a single system, which is the engine through which the universe evolves. To do so, I also had to travel not just in space, but to travel in time, because I want to show you what started from the very beginning. In the very beginning, the universe was looking a bit like this, and all those filaments that you see are part of the dark universe. These are filaments not of regular matter, are filaments of dark matter. And dark matter is in fact most of the matter that appears in the universe. About 1/5 of the total is the regular matter, all the rest is dark matter. And what happened with the dark matter is that it constitutes a way of the matter in the universe to start to come. Because dark matter is such that it doesn't interact with light, it doesn't interact with nuclear forces, it only interacts with gravity. So dark matter is the first of the matter of the universe that managed to collapse under its own gravity and form this kind of structure. At the time, there weren't really, there was this matter was available, but the only atoms that could form at the time were atoms of hydrogen and helium. So the universe, if you want, at the beginning was kind of boring. There was only this gas, hydrogen and helium. There were no stars. And that's why we call this the dark ages of the universe. And could have been stuck like that, except that the universe found a way of forming more kind of atoms and become a little more interesting when finally the stars managed to form. Now, the people that realized first how those first elements were formed are the three guys in this picture, alpha, beta, and gamma. In fact, the work was done only by two of them, beta and gamma. But beta was a joker. He decided, well, it would be cool if I can call the paper alpha, beta, gamma. So they asked their friend alpha if it would be on the paper. And he said, okay. So what did they do? They were the first people the first scientists to understand that at the very beginning, shortly after the Big Bang, the universe became cool enough that all the goof that was in the universe at the time, we call it quark gluon plasma, but essentially is the particles that eventually coalesced into the component of the atoms, neutron and protons, together with the electron. They were the first to realize that when the universe became cool enough, the atoms could form out of this elementary particle. Now, in their paper, they thought that all the elements would form at that point. And that was actually not correct. The correction came a little later by four people, Apple, Margaret and George Burbridge, together with Fowler and Hoyle. They realized that, in fact, the Big Bang could not have formed all the elements. Only the first two, only hydrogen and helium. All the other elements, which are heavier, more complicated to assemble, there was not enough, the conditions in the universe was not enough to do that. So the question was, okay, where are all those other elements coming from? And the answer is stars. They were the first scientists to realize that all the other elements after hydrogen and helium were the result of nuclear reaction inside stars or nuclear reactions that happens when the stars are dying. And I don't want you to learn all those nuclear reactions, but the basic idea is that you take the hydrogen and helium, you smash them together, and then you form nuclei which are bigger because all those particles stick together, so you form a heavier nucleus, and then you smash that with another one, and you kind of climb the periodic table. And you can form all the elements that we see today. Now, said like this, it's kind of easy, but in practice it's not, because the star cannot really form all the elements. Stars only have a certain kind of nuclear reaction that they can do. And so going from the original hydrogen and helium to the entire periodic table requires different passes in different kinds of stars. And that's why you need something like a galaxy that possesses the engine to make all those steps. Okay. So we need stars. And how do you form stars? Well, you have gravity. So the gravity mainly due to dark matter. So as soon as the universe was cool enough for the regular matter, this hydrogen and helium, to fall into the gravitational potential of the dark matter, they started to form what you see this in this simulation, which were the first galaxies. So the first galaxies were essentially the result of this hydrogen and helium falling inside along the filaments of this dark matter, getting more and more concentrated until you manage to form the first stars. Now, astronomers will think of going with the convention that sometimes they don't seem to make much sense. But so this is the first generation of stars. We still call them population 3. Why? Well, because this was the third population of stars that was discovered. But in fact, these were the first stars that were able to form out of pure hydrogen and helium. And it means that these were very heavy stars. They could be something like 1,000 times the mass of the sun. And if you look in the simulation, you see that there is all this green. That green is a tracer of iron in this simulation. So these first stars were the first that actually managed to fuse hydrogen and helium into a heavier element all the way up to iron. And then at the end of their life, release all this material into interstellar space, and even in this case into the galactic space, to seed the gas that is there, so that the next generation of stars that will form out of that will be able to start with a higher content of heavier elements. Now, these were very massive stars, so I guess you know by now what happens when you have a massive star, right? Well, we'll see that in a moment. Now, the Webb telescope was actually, well, it has many missions that it has to accomplish, but one of the main missions that influenced its design was precisely to find this first generation of stars, population 3 stars. Now, they find it yet? Well, sort of. So, this is an artist's impression of a faraway galaxy that you can see now that was when the light that we now see was emitted. This galaxy was in the very young universe. And you see that there are different kinds of stars in the simulation that corresponds to what we see in the actual image that Webb has taken, which is this one. So this is just this. Okay, but it's so far away we cannot see the individual star. What we can see are the big blobs of the light collectively emitted by the stars in this galaxy. And you see that they are color-coded in different way, but that's because Webb was looking at some specific color in the emission of the light from those the stars in the galaxy that we can do to try to figure out what kind of stars were there. And this blob in green is corresponding to a very specific line of hydrogen, which our models show was only emitted in that large amount from population 3 stars. So what we think is that this area, which in the artistic representation corresponds to this, is precisely a population of stars which contains mainly those first stars that were responsible for performing the first step in populating the periodic table from the original hydrogen. Now, as I was saying, you should know by now what happens when you have a big star that ends its life. But what happens is the supernova explosion. So the supernova explosion that we see in the stars, in the massive stars that we have in our galaxy now, they're pretty impressive. They can, you can see them from the other side of the galaxy, but you can even see them actually from very far away galaxies. Supernova is what we use to measure the distance far away in the universe because they are such a bright beacon. And that's nothing compared to the kind of explosion that these first stars are making because, again, these were at least 10 or more times more massive than the most massive stars that you can see today in the universe. So the mechanism in which these population 3 stars managed to seed the universe with the product of their first occurrence of nuclear fusion is precisely the explosion of this gigantic supernova at the end of their life. And it didn't take very long because stars this massive, they go from birth to death in less than 1 million years, which for us, it's kind of a long time, but compared to the age of the universe, which is 14 billion years, that's really not very much. So as soon as those stars forms, if you think in cosmological times, they already died and were able to see the universe with heavy elements. Now remember also what happened when we have all those shock waves, explosion, and strong wind from big stars. What happened to the surrounding material? The surrounding material typically get compressed and to the point that it may form a new generation of stars. And this is precisely what happened when those population 3 stars die. You add enriched material, which has these elements that were produced by the first stars, which was again in the condition of forming new generation of stars. So this is what we call the population 2 stars. For the first time in the history of the universe, now you have stars which don't have just hydrogen and helium, but also have heavier elements. Not much, not like the sun. The sun has much larger concentration of heavier elements, but still enough to make a difference. Now, we still see population 2 stars in the Milky Way. They tend to be not on the plane of the Milky Way, so the Milky Way that you can still see in the dome, that's correspond to the disk that you were seeing before, the rotating disk where most of the stars are now. But population 2 stars, they tend to be in a kind of a spherical halo, spherical distribution around the galaxy. If instead you look at the disk itself, that's where you find stars like the sun, what we call population 1 stars. Those are the stars that manage to form out of the death of the largest of the population 2 stars. And so they form out of material that was even more enriched than the second generation stars. And these are the stars like the sun that have a composition where you can find essentially all the elements in the periodic table. Now, before moving on, I want you to show something. So this is the image. It's an actual image of the Milky Way. If you had a spaceship going with a very strong warp drive, you go outside and then you look at the Milky Way from outside. Is not an artistic impression. It's a model made with data from the Gaia satellite, which is a satellite that mapped the Milky Way, precisely recording the position and motion of billions of stars in the Milky Way. And then with the computer, scientists in Europe were able to reconstruct the 3D distribution of the star in the Milky Way, and this is exactly what you see. So I want to show you something. It's difficult to see because the dome is curved, but the plane of the Milky Way is not actually plane, it's actually warped. And this works because galaxies like the Milky Way, they don't live in isolation. They live in community with other galaxies. Remember the simulation at the beginning where there were all these galaxies mixing and flying around? Well, it happens still now. The Milky Way has some satellite galaxy. The two biggest two are called the Magellanic Cloud. You cannot see them from here. You have to go to the southern hemisphere. There are many. And then we have the Andromeda Galaxy, which is the next neighbor. This community of galaxies often interact one with the other. They exchange material. So when I talk about ecosystem in galaxy, I actually mean even ecosystem between galaxies. Because galaxies interact, they can do these things like the forming, the shape of the galaxy, warping the disk. Sometimes it's much more dramatic. At some point, the Milky Way will collide with the Andromeda Galaxy, and then we will get something which will be nothing like the galaxy that we live today. So this process is actually quite important also in the way they trigger new generation of stars, because there is gas exchange between galaxy and another. There are compression of the gas when the gas clouds from one galaxy collide with the gas clouds of the other galaxies, and so on. So what we're talking about then is a comprehensive system where the various elements that I described so far fits together. So you start from those nebulae, which either because of internal processes or because of external processes, like influence from another galaxy, or influence because there was a supernova that exploded nearby, or maybe because there were these hot stars that compressed the gas. These dark nebulae then start to form stars, so you have a star formation nebula, star formation cloud. Depending on the condition, you can start to form high mass stars or low mass stars. That lives their life. The high mass stars, they die quickly and then explode the supernova, like the one that we saw at the beginning. The less massive stars, like the sun, they don't explode the supernova. They do this nebula that in some cases become planetary nebula. But in both cases, even though with different timing, the result of the nuclear burning is returned to the interstellar medium. It's hot at the beginning, then it cools down until it forms a new dark cloud, out of which a new generation of stars can form. So it's a cycle in which every time you go to stars, you start to produce more elements, and the composition of the heavy elements in the nebula becomes higher and higher. So this is the way the galaxies manage to increase the variety in the quantity of the heavy elements that they contain. So the end result is this, which is nothing else than the periodic table of elements. The idea here is where you order the elements based on their chemical properties. This is a very interesting periodic table, though, because you see that it's color-coded. And the colors represent which of these environments in a galaxy are the source of these elements. I want to show you now how all those locations that you saw actually contributes to different parts of the periodic table. We start from the first two. Okay, this has nothing to do with stars. I now know it. Hydrogen and helium, those are the result of Big Bang nucleosynthesis. The plasma that you had at the beginning, quark gluon plasma, that cools off and start to form the elementary particles that then form protons and neutrons that then assemble together in forming hydrogen and helium. But these are the only two that are not due to the activity of stars. Because then, remember, population 3 stars, these are the first one to die, big gigantic supernova explosions. The kind of nuclear processes that happen in this supernova explosion actually are able to contribute to all the elements that you see here, at least the yellow fraction of all these elements. And these are important elements like oxygen, fluorine, neon, potassium, calcium. Some of these elements are quite important for life. Even in life, there was oxygen. So most of these elements are originated either by the explosions of these population of stars or by the explosion of the supernova that happened more recently when a new generation of massive stars had been formed. This one, well, There is other two elements that actually find their origin in supernova, but not in the supernova explosion stars. Now, when a star explodes supernova, typically you have also the emission of gamma rays. You may have a gamma ray burst, they're called. Gamma rays are is light, that is light of very high energy, so high that it behaves almost like particles. Okay, the light of gamma rays really patch. So strong is in fact that are capable of accelerating particles like a natural accelerator when they hit those particles and form what we call the cosmic rays. So Earth is constantly bombarded by particles that come from space. Most of them come from the sun, because there is solar wind, but the most energetic one comes from deep space. And the origin of cosmic rays is precisely the supernova remnant and the neutron star that is at the center that acts like a natural accelerator and accelerates those particles. When these particles, and then also the gamma ray, hit the atoms that they see in the interstellar medium, they can trigger nuclear fission. And as a result, you get smaller atoms. And in particular, you get two atoms that stars otherwise would not be able to find, to form, which is boron and beryllium. So boron and beryllium, and I didn't highlight it, but also some of the lithium, are actually the origin, actually formed by cosmic rays that induce nuclear fissions on the atoms that instead, larger atoms that instead stars are capable to form. Next one. Well, what happened to the Loma stars? Again, they don't explode as supernova. They do have their own different stages of nuclear burning. They burn hydrogen to more helium, and then the helium burns to carbon and oxygen, and then they kind of stop, except that they have a very particular mechanism of intermittent burning of the hydrogen and helium in their interior, which produce a lot of neutrons, and these neutrons stick to the atoms that are around, making them bigger and bigger. These are typically elements which are radioactive, so they decay. And when there is radioactive decay, you have one of those neutrons that becomes a proton. The bottom line is that that's another way the stars have to climb the periodic table. These periodic nuclear reactions form all the atoms that you see here with marked in green. And these are kind of important because, you know, most of the carbon and nitrogen were actually formed by the burning or by the nuclear burning in stars like the sun. Other elements are important. Okay, these are called S elements because they are produced S dense low, because they are produced slowly in this intermittent burning that happen over a million years or so at the very end of the life of these stars. There is another way in which the Loma stars actually manage to form different kind of elements. Remember the white dwarf? Sometimes those white dwarfs live in pairs, in binary system, and either maybe there are two white dwarfs, or maybe there is a white dwarf with a star, which eventually, as it evolves, will become a giant star, big star. When that happens, there may be a transfer of mass between the star and the white dwarf. So the white dwarf becomes heavier and heavier and heavier until, again, it cannot support its own weight and collapses, similarly to the way that supernova or massive stars collapse. So this is a different kind of supernova. It's called supernova type 1A because they have a different spectral signature when we observe them than the collapse supernova, the collapse of massive stars. So the kind of nuclear reaction in this case are different, and the elements that are produced in this process are the one that I have highlighted in white. And you see a lot of metals like iron, cobalt, manganese, nickel. These are the product of the explosion of white dwarf in binary system that ate too much from their companion and then exploded. Neutron stars, the result of the burning, the result of the explosion of a core collapse supernova, these are the massive stars, they also have a last trick if they are in binary system. If you have binary neutron stars, they typically orbit one around the other, but they're very heavy, so they emit a lot of gravitational radiation, and as they emit radiation, their orbit ends up decaying. That's because a lot of energy is lost in the production of these gravitational waves. And at some point, they touch one another, and they collapse. What is the result of the collapse? Typically, it can be a black hole. Okay, because the mass that you concentrate at the center is so big, there is no way for all the forces in nature to hold the weight. So the thing keeps collapsing until it basically punches the hole in space-time, and you get a black hole. But in the explosion itself, a lot of material in the external layers of those collapsing neutron star, or those merging neutron star, are ejected in space. These look like supernova, and the kind of elements that are produced in this way are also quite unique. Most important of them probably are the metals like gold, platinum, all the precious metals that are produced in this way. You basically won't have almost any gold for merging neutron stars. So in this way, we can essentially explain all the elements that you see in the periodic table. If you have a keen eye, you will notice that there are some elements that I didn't highlight at any time. There's one color that doesn't match the. You see it? Yeah, so this one that does in brown. You know why? What is the source of those elements? Yeah. Some of them are so heavy that it's difficult to find something to decay. Yes, these are artificial elements. So we are, if you want, we are the last step in this galactic ecosystem because we managed to form elements that would not be able to form otherwise. Now, that's not entirely true. There is at least one of the elements that is formed in stars, using stars like the sun and the end of their life, which is technetium. Now, it was not discovered in the stars, it was discovered in the lab when it was artificially produced. But this is actually one of the elements that you can produce slow climbing of the periodic table. And in fact, when you see the signature of this element in the spectrum of the star, then you know precisely that exactly the star in this moment is going to the stage in which those elements are produced. But apart with that exception, all of the others have been produced in the lab. In fact, there are many more than those. We stopped at 94, but actually there's an entire other row that has been continuously. It's very difficult to produce those elements because they're not stable, they're radioactive, they last only a very short time. The golden grail would be to find one stable element that is artificial. There are some models in nuclear physics that suggest that there may be actually what we call the island of stability, that if you go far enough in adding neutrons and protons to this element, you will reach that and you find the artificial experiment. But so far, it's been out of reach. So the conclusion of all this is that these galactic ecosystems are the way that the universe has to form the elements that we see in the world now. We wouldn't have planets if there weren't stars that produce the elements that form planets, like the silicon for the rocks, the oxygen, the atmosphere, the nitrogen, and the carbon. Especially the carbon. The carbon is very important because, as you know, is the element that is at the base of life. So the end product, really, of these galactic systems is not just the formation of planets, but also the formation of life on this planet, and ultimately us. So you can think of all this as a way that the universe has to reach a point in which it can stare at itself and look at its origin, trying to understand what we are made of and where we are coming from. That's the end. Questions? Don't be shy. Yes. Sorry? The random is actually, you can have it's a radioactivity or uranium. Yes. Second exception. Oh, that's the Rubin telescope. So this is a very new telescope. It's in Chile, and it has been built. It's just in the commissioning phase now. It just started to take images now. So the telescope is it's been made by was made by the National Science Foundation, and the objective of this telescope is to take a movie of the sky. So the telescope itself is built like a wide-angle lens, and it is very efficient in mapping large area of sky continuously. So essentially, it can map the entire sky that you can see from Chile at any given night in 3 nights. So in 3 nights, it maps the entire sky, makes a map of the entire sky. So you repeat it doing it over and over and over, and then you can see what changes. That's why I'm saying it's like a movie of the sky. Why? So what do you want to do with this? Well, we want to look for transient, for example, like supernova. We want to see supernova far away because the one interesting characteristic of supernova 1A, the one that are the result of exploding white dwarf, is that they work like standard candles. Essentially, they have a fixed luminosity. You know what is the intrinsic brightness of those stars when they explode. And then you measure how bright they appear to be. And then, if it appears fainter, then you should be, because that's farther away. Basically, you can use them as a ruler to measure distances on cosmological scale, because you can see those very, very, very far away. And in fact, the mapping of the local universe with supernova 1A is exactly what was used to measure the acceleration of the universe. I should have said they try actually to measure the deceleration of the universe, because at the time people thought that the Big Bang has sent everything out, but then there is gravity, and maybe this should slow down because there is gravity is pulling it back. To their surprise, they found that instead the universe was accelerating. And the reason for that is that there is a force that nobody knew existed at the time. We still don't know what it is, but we don't know what dark matter is. But even this force that is pushing the universe apart and making it accelerate is what we call dark energy. It was precisely discovered by looking at supernova. So Rubin will be researching a lot of them, but many other things. Like, for example, it has already found hundreds of thousands of solar body new asteroids. Because you look at the sky, all these things moves. And then you can reconstruct the orbit, and then you can find the object in the solar system that you wouldn't see otherwise. Or you can see variable stars, like pulsating stars. The stars like the red one with all the rings, is actually pulsating. And that's why it forms rings also. Okay? It's an effect of the fact that the luminosity is and decreases periodically. And we want to know all those, we want to find all the stars that are changing brightness, because they also have very interesting properties. This is actually what I do for my research. You can use them to understand their chemical composition. You can also use them as standard candles, because the period that it takes for the light to go up and down is proportional to how bright they are. So again, measure how bright they appear, you know how bright they are because of the period, and you have the distance. These are in fact part of the distance scale ladder that is used to measure distances of cosmological scale. So Rubin will be able to find hundreds of thousands of them. Other questions? There.
Yeah, I know you're very two variations of Galactic for thorium 234.
Yeah.
So thorium 234 doesn't it debate decay and go to proof activity when it's in brown?
Yes, so let's put it this way. All those elements that were drawn in brown are the elements that are not produced in stars.
Okay.
So
they could be produced by radioactive.
they can produce by radioactive decay, but typically the lifetime of the radioactive decay is relatively short.
Right. So
with the exception of the technetium, which is few tens of thousands of years, something like that, every other element that is radioactive is quick to decay. So even if it is produced by the radioactive decay of a star, of the elements produced in a star, by the time you're observing them, typically they are gone. So it's a very good. Yes.
The things that people want us about the company.
What was it exist? Because astronomy was a branch of physics, and physics is based on experiments. Unfortunately, we cannot run our own experiment in the lab because it's kind of difficult to make a star in the lab. So we are forced to use the experiment that nature gives us. So we make models for the material, but in fact, they are models, mathematical models of how things should happen. And then those models may be wrong. The only way of knowing for sure is actually to see that the thing is really happening in the sky. In the case of those first stars, we have the basic idea on when they appear, based on other kind of data. But what happens is that when we turn on AWST, well, the first image, if you remember, there was a press conference that was the White House at the time. They showed the first image was a deep field where galaxies, it was a relatively short, few tens of hours, image of a dark patch in the sky, and everything you were seeing there, except for a couple of stars, were galaxies. And you could see galaxies far back in space, which means also far back in time. So the first image already was a surprise because those first galaxies, which are galaxies with presumably are made mostly by populations of stars, they appear to be bigger and more massive than our models predicted. That's not been completely resolved yet. So we know more or less what should have happened, but the details are not obvious. And the only way to straighten up the details is actually getting data and try to, sometimes the models are wrong. We have to throw them away and start from scratch. In many cases, maybe we only have to tweak the parameters. The model of cosmology, we call it lambda CDM. Lambda stands for dark energy. CDM stands for cold dark matter. Is an accepted model. It is able to explain quite in detail how the universe evolved. But when you start to look at the fine point of the model, there are things that don't work quite well. Like, for example, how quickly the universe is expanding, Hubble constant. Different methods produce different numbers. And we don't know exactly why. I'm not 100% sure that's the case because it's a number which is difficult to measure, but now we are at the point in which it becomes difficult to ignore. So maybe then the model is wrong, or maybe the model is incomplete. That would be very exciting because it means that there is some physics which we don't know. That is the reason why this measurement doesn't match. So the idea is that's why we are getting data with this bigger, more expensive telescope, because we reached the point in which we are at the stage now in which we need data to be able to test those models, which we wouldn't be able to understand otherwise. The questions? Yes.
Why are you talking?
That's a very good, that's a very good question because there is a limit in the stars that you can see in the universe today, how big, how massive they can be, which is the order of 100, 120 solar masses. So the mass of the sun, 100 of them. And the reason why now you cannot go past that is because stars with that mass, they are so luminous that the light essentially blows away the external layer of the stars. You don't feel it, but light actually has a pressure. So to the point that you can actually navigate space using solar sails. Basically, it's a gigantic, very thin and very light sails. And we have already tried with a couple of satellites. We deploy the sail captures the light from the sun in this case, and the light actually exerts a pressure and manage to move the spacecraft. So you can actually navigate space with sails. And it's not just the sail that feels the radiation pressure, but also atoms, including the atoms that exist in the atmosphere of stars. So if a star is too luminous, the radiation pressure is so strong that basically the external layer of the star are going to go up. You cannot accrete more. You cannot go past this 100 or so solar masses. However, those first stars, the population of these stars, were much more massive than that. So how did they do it? And the reason is that those original stars only had two elements, hydrogen and helium. And it turns out that those two elements are relatively transparent to radiation. So the atmosphere of these stars was thin enough, so transparent enough, that the radiation pressure didn't have anything to hold on and could pass through. So you could reach much higher masses. That's why we have stars that at the time had maybe 1,000 solar masses. So strangely enough, the bigger stars are less dense than the smaller stars, even though they have much more mass. But they produce so much energy that they are puffed up by just the heat that nuclear reaction inside produce. Instead, smaller stars are more compact, more in terms of less massive stars, are more compact because they produce less power, less nuclear power, so they settle on radii which are small. And in fact, the smallest stars, we call them M dwarf, M just is a way of classifying the characteristic of their spectrum. Those have sizes which are comparable to the sizes of planets, like Jupiter. Maybe a little bigger, but not much bigger, even though they are stars. Okay? They are not producing energy to the fusion because the brown dwarf, they never managed to burn anything past the deuterium, which is one isotope of hydrogen. But they're not planets. I mean, they're really stars that fizzle pretty quickly, but we're stars. But they're the size of Jupiter. Yes. Remember the star with the red rings? So that is a giant star. Now, it turns out that stars like the sun, they go through two different phases of being a giant. So you have the star that is burning hydrogen, like the sun now. At some point, it will run out of hydrogen, and then it will start to, the core, mainly because the hydrogen in the sun is burned at the center, which is the hottest part, the denser part. And but at some point, all the hydrogen at the center will be replaced by helium because you burn hydrogen, you produce helium, and then you run out of hydrogen to burn at the center. So what happened is that at that point, the burning transfer from the center to a shell of hydrogen, which is around the core. So the core is extinguished; it's just a core of helium. For stars like the sun, it's not even gas; it's more close to a solid than a gas. And so it's very hard. And on top of that, you have the hydrogen that is still burning in the shell. The burning of hydrogen in the shell is much more efficient. First, it's a different chain of nuclear reaction than the one that the sun is doing now. But most importantly, it's efficient because given that there is this solid core at the center, this shell is squashed by the rest of the star, so it reaches conditions to burn more efficiently. And when that happens, so there is a lot of energy that is suddenly produced. So the sun, by definition, produces one solar luminosity, the unit of luminosity of energy per unit of the power of the sun. When the sun becomes a giant, you go from that to something which is 100 times more. And that's why the sun becomes a giant, because suddenly you have all this energy that is produced. The external layer of the sun, they don't know what to do. It's very difficult to dissipate all that energy. So in the case, so what happened basically is this energy cannot escape so easily. So the star essentially starts to boil. You know when you have a pot of hot water on the stove, and you have this motion, convective motion, which says that of hot water that rises from the bottom to the top and then goes down. The water is boiling. Something very similar happens to stars in this stage. The energy cannot be easily irradiated away, so the external layer of the star becomes to move in this convective motion. And when that happens, the radius of the star becomes bigger and bigger and bigger. Again, by a factor of 100 or so, even more, with respect to the original radius. That lasts only up to the point in which this hydrogen shell can burn. At some point, the star, because you remember, it's burning hydrogen, so it's producing more helium. This helium is deposited into this core. At some point, there is so much helium that is deposited in the core, it's compressed so much that it ignites, and you start to burn helium. And the star leaves the place where you can see the stars in the luminosity radius diagram or temperature diagram. Basically, they stop to be a giant, they become smaller, and they become what is called a core helium burning star. They stay there for a while. In the case of the sun, maybe like 100 million years, which is a lot, but it's also short because the sun will stay burning hydrogen in the core for 10 billion years. Okay, so it's a shorter time, during which they will burn helium, and they will burn helium producing carbon and oxygen. So you're gradually replacing the core of helium with the core of carbon and oxygen, which also is a similar condition. It's kind of solid, okay? Solid state forces up in there, quantum mechanical forces. And until there is no more helium to burn, and then you get in a similar situation. You have this core that is inert, because stars like the sun, they will never be able to burn carbon and oxygen. There's not enough mass to compress them to burn. So the burning stops at the core, and you start to burn helium and hydrogen in two shells around the core. Again, more efficient, a lot of energy, stars expands again, that becomes an asymptotic giant branch star, basically second life as a giant for the sun. And when that happens, the luminosity will be even bigger. It's something like 10,000 times the luminosity of the sun now. That star that I showed, the one with the rings, is an AGP star. It's precisely one of those stars that is in the second stage of being a giant star. Yes.
I just find it's only build up to the fire as mission. And on the video, so special.
Iron is special. The reason why it's special is because if somebody try to sell you a nuclear reactor to use iron, don't buy it, because it will not produce any energy. In fact, it will consume energy. So the way energy is produced in a nuclear reaction is that they basically convert mass into energy. Remember the Einstein equation, the one that is on the t-shirt, E equal to mc squared? Basically, that means that there is energy associated to mass, and a very little amount of mass actually, if you manage to convert it into energy, it's a lot of energy. So when you're taking hydrogen, like 4 nuclei of hydrogen, and you squash them together, you can get a nucleus of helium, which is 2 protons. The proton is the same as the nucleus of hydrogen, and 2 neutrons. And the neutrons are different than the protons because they are neutral, they have a charge. The way of getting a neutron from a proton is to get an electron, proton, squash them together, you get a neutron. Or inverse beta decay. It's like nuclear decay, but the other way around. So you start from 4 protons and you get a nucleus of helium. If you weight the 4 protons, and if you weight the nucleus of helium, it turns out that the 4 protons, the sum of the mass of the 4 protons is higher than the mass of the helium. So where did the mass go? Then the energy that is produced in the fusion reaction. And that's why we really like a fusion reactor, because hydrogen is very easy, you get everywhere. If you manage to fuse it, you will produce a lot of energy and very little radioactivity. It would be nice. Okay, hard to do. It's easy for a star, but for us, not so much. So, stars, you heard me talking about how you start for helium and then you form carbon, oxygen, and so on. You can keep going. A star like the sun will not go past the carbon oxygen stage, but the more massive stars, they have enough self-weight that they compress this carbon and oxygen, start to ignite them. So you can go past in the periodic table the carbon and oxygen. And you go, in fact, all the way to iron. Now, with iron, something catastrophic happens. Because if you take two nuclei of iron and you squash them together, you will get a nucleus which is bigger, more massive. And it turns out that, more massive in the sense of more particle, but if you weight the product of the fusion of iron, the weight is actually more than the weight of the atom of iron that you're fusing together. That means that if you fuse iron, instead of producing energy, you're consuming energy. So think of it this way. You have this big star that's gone all the way to produce a lot of iron. By the way, these final stages of nuclear burning, the one that goes from silicon to neon to iron, they happen very quickly in terms of weeks or hours last stage. So it's a very rapid process here. Then you get to the iron and say, okay, now I get the big nuclear. I'm very excited. They try. And what happens is that suddenly they find themselves without the energy that is necessary to heat the plasma that is producing the gas pressure that prevents the star from collapsing under its own gravity. That's when a core collapse supernova is triggered. So, supernova happens when those massive stars have gone all the way to iron. Now, if this was the whole story, we would not have any elements that is heavier than iron. However, the processes that happens in the collapse itself, and the processes that happens when you have this complicated shell burning in AGB stars, in the second time giants, and the process that happens when you merge neutron stars or you make a white dwarf explode, those are able to get past the iron. The way they do it, though, is not through nuclear fusion. Basically, you have a heavy nucleus. Then, when these catastrophic events happen, you typically produce a lot of neutrons. In fact, the result of a supernova explosion is a neutron star. Sometimes it's a black hole, but in most cases it's a neutron star. Neutron stars are made just by neutron. Basically, when the collapse happens, the matter is compressed so much that the plasma, which is made by the fragmented nucleus of iron and so a lot of protons and neutrons. So the neutrons are left alone, but the protons are squeezed together so much that they are all converted together with the electrons into neutrons. So basically, the entire core of the star becomes just a big ball of neutrons. That's what the neutron star is. These neutrons, however, they're not only compressed at the center, they are flying everywhere. So when these neutrons that are flying everywhere hit the heavy atoms that have not yet been destroyed, they plant themselves inside those nuclei. Typically, you get some radioactive element. This is not a stable process. So you get from iron, and then you start to gather more neutrons. In the case of a supernova point, you can put many neutrons in quick succession. This process is called R process, for instance. R stands for rapid. So what happens is that this nucleus suddenly becomes to start to have a disproportionate number of neutrons is the radioactive nucleon, because all those neutrons cannot be stable beside the nucleus, so they start to decay. When you have decay, this is the regular beta decay that like uranium does. One of those neutrons goes back to being a proton and an electron. The electron leaves and the proton stays. So the end result is that you start with a nucleus which is a certain number of protons, and you get nuclei which have higher number of neutrons or protons. And that means you are climbing up the periodic table past the iron. And you can do that all the way to the end. But of course, it needs a lot of neutrons. So that's why it happens when you have these gigantic explosions. Yes.
Wow. Show me what color it was.
Matters, yes. What you want is to transfer the momentum, you know, to the moment. The momentum is the capacity of an object in motion to transmit the motion. So you want to transfer the momentum from the light, the photons, the particle of light, to the sail. And so if you have a black sail, it will absorb all the photons. So all the momentum is transferred to the sail. That would work, but that's not the best way. If instead the sail is made like a mirror, we have this light that is coming in, is hitting the sail, transferring the momentum, but then the light is reflected back. And the angular momentum in total needs to be conserved. So if you start with the momentum in this direction and apply the momentum in this direction of the light, it means that the sail has acquired twice as much momentum that is just absorbing the momentum of the photon. So the best way of doing that is really making them like mirrors. In this way, the light bounces off the sail, and the sail gets more impulse. Now, this has been done as an experiment. I think there have been two experimental satellites that have been used. They're very difficult to do because they need to be very, very large. The light doesn't really have a lot of impulse. But it's feasible. In fact, there is a conceptual study that would like to use those sails to send a spaceship to the next star, Proxima Centauri. They work like that. Basically, you deploy a very, very, very big sail, and then you use gigantic lasers in orbit of Earth, and you shoot the laser to the sail when it is still close. A lot of energy in a very short time, and you know, before the sail becomes too far that even the laser cannot do much, you manage to accelerate it to relativistic speed, meaning speed comparable to the, you know, maybe a fraction of the speed of light, but fast enough that you will be able to get to Proxima Centauri in like 100 years.
We have a last question.
Hey.
Last question.
The Cat-5. The Cat-5 is a nebula, yes. So it's a different planetary nebula, not the one that I showed, which is the Ring Nebula, but is another planetary nebula. So the result of stars more or less the mass of the sun that at the very end make this fluorescent light with the materials that slowly eject. It is called Cat-5 because if you look at the telescope, it really looks like the eye of a cat. The problem is that, and it's true also for the Ring Nebula, the Cat's Eye Nebula is not round. They're called planetary nebulae because with the early telescope they were looking like circle. But when Hubble started to observe them, they realized that they were all weird shapes. And in fact, the Cat's Eye is not a circle; it's a kind of a cylinder. They're just happening to sit to the bottom. And they're all like that. And the reason is that to form those things, you need to have two stars. So the sun will not become a planetary nebula. You need two stars that spin the material around, and they put it in the right place at the right time so that they can brighten up like planetary. So there are still like 6 billion years to go, so the particular problem is for us, but unfortunately we will not see that spectacle. Also because by the time our people will be incinerated. Thank you for coming tonight.